Hello everyone, this is Yuxiong He. I also have my colleagues Sanyan, Jeff, Tanji here today. We are all from Microsoft DeepSpeed team. Our team has a group of system researchers and engineers who are enthusiastic about performance optimization of large-scale systems. Recently, we have been focusing on deep learning systems, optimizing its speed to train, speed to convergence, and speed to develop. That leads to our work on DeepSpeed, a DL training optimization library towards speed and scale. We will give you a deep dive of the work today. This is the outline of the talk. So first, I'll give an overview of DeepSpeed, why we develop it, and what it is. Then I'll describe highlights of the result and the underlying techniques, as well as the software architecture. After that, Jeff will talk about how to use DeepSpeed. Then Sanyan will walk over Turing-NLG 17 billion model training as an example. Over there, he will highlight some key techniques like ZeRO, flexible combination of parallelism. Then Tanji will give you another example on the fastest BERT training. We will conclude the talk with upcoming features. So as we all know, DL training is challenging because it's too slow to train high-quality models on massive data. More specifically, more hardware may not bring higher throughput. For example, when communication is a bottleneck, when model size exceeds device memory. Furthermore, higher system throughput may not indicate faster convergence. This is where the dark part of deep learning kicks in, where techniques such as large batch scaling, gradient compression improves performance but could slow down convergence. The last but not the least, the optimization ideas and techniques are often scattered. How to use them collectively and conveniently is non-trivial. So all these challenges motivate our work on DeepSpeed. DeepSpeed strives for 3 E's: efficiency, effectiveness, and easy to use. Efficiency promotes efficient use of hardware for high throughput on single device and scalability across multiple devices. This is the HPC part of DL systems. Effectiveness promotes for high accuracy and fast convergence. We reduce the number of samples needed to achieve high accuracy, lowering training cost. This is where machine learning theory intersects with the system part. Thirdly, easy to use makes the earlier 2 E's conveniently accessible to our model scientists to improve their development productivity. So what is DeepSpeed? DeepSpeed is a DL training optimization library. On the software stack, it sits between DL models and training framework. Among training frameworks, we primarily support PyTorch. PyTorch user can leverage DeepSpeed with just a few lines of code changes. Here is an example that the left-hand side is BERT original and the right-hand side is BERT with DeepSpeed. As we can see, the primary change needed is to call DeepSpeed.initialize to wrap the model and parameters. Then we can use wrapped model as DeepSpeed engine to perform forward pass, backward pass, parameter update using similar syntax as original. That's it, just a few lines of code changes. Then DeepSpeed will handle the underlying performance challenges, apply efficiency and effectiveness optimizations as appropriate. That leads to speed and scale. What kind of speed and scale? DeepSpeed excels in 4 areas: model scale, speed, result scalability, and usability. I will talk about them one by one. First, with respect to model scale, state-of-the-art models like NVIDIA Megatron LM, Google T5 has about 10 billion parameters. DeepSpeed introduced a system breakthrough, ZeRO, standing for Zero Redundancy Optimizer, to conquer the memory and scaling challenge of very large models. ZeRO significantly reduces memory footprint while retaining compute and communication efficiency. In the first stage, ZeRO1 imparts deep speed to run 100 billion parameter models efficiently, 10x bigger than the largest published models by then. Leveraging this unique system capability, DeepSpeed powered model training of Turing-NLG 17 billion parameter model, the largest model until last month, and obtained record-breaking accuracy. We continue to push for the frontier of training systems. In early May, we released ZeRO2, which adds novel optimization on top of ZeRO1 and unblocked 200 billion parameter model training on today's hardware. Very recently, we heard GPT-3 from OpenAI. It has a record-breaking model size of 175 billion parameters. I want to point out that the system capability of ZeRO2 would allow us to run such gigantic models. Furthermore, we are working closely on ZeRO3, which could allow us to scale to models of arbitrary size as long as the aggregated memory of hardware allows. For example, running 1 trillion parameter model using 1,000 GPUs. Please stay tuned for that. Besides scale, DeepSpeed also excels in speed. For very large models, such as those over 25 billion parameters, we observe up to 10x faster throughput over Megatron-LM, a state-of-the-art model parallelism approach. For example, the figure here shows a system throughput using DeepSpeed versus Megatron-LM. The workload is a GPT family of models with size from 40 to 117 billion parameters. Here, the throughput of Megatron-LM is normalized as 1x, shown as green bar, and the throughput of DeepSpeed are shown as blue bars. Megatron-LM uses tensor slicing for model parallelism, primarily optimized for intranode parallelism. But for model of such size, it needs to run them across nodes. Then the limited internode network bandwidth significantly degrades performance. On the other hand, DeepSpeed combines zero-part data parallelism together with tensor slicing of Megatron. So ZeRO improves memory efficiency. It fits models using lower degree of model parallelism and allows for larger batch size, improving both computation and communication. That leads to up to 10x higher throughput. On the third part, with respect to scalability, we have some interesting observations. So for people working on systems, it is normal to see sublinear speedup with an increasing number of devices. Perfect linear scalability is probably the best to expect. Can we do even better? The answer is yes, sometimes with DeepSpeed. So the figure here shows our system scalability with an increasing number of GPUs. The green curve shows the scalability assuming perfect linear speedup, and the blue curve shows the measured scalability results of DeepSpeed. We can see that our measured scalability is above the perfect linear speedup line, achieving superlinear speedup. In other words, when we double the machines, we more than double the system throughput. So what's going on? This comes from the power of ZeRO. When we increase number of GPUs, we reduce the memory required per GPU to store model states. So there are more device memory available for activations that allows higher batch size and potentially higher GPU efficiency, and it brings superlinear speedup. When we scale models towards many devices, such superlinear speedup could reduce the training time substantially. Last but definitely not the least, DeepSpeed is easy to use. As we have already seen, just a few lines of code changes, we could enable DeepSpeed on PyTorch models. Furthermore, to train large jobs, model parallelism is a major constraint. We alleviated that burden from developers. So for models up to 13 billion parameters, DeepSpeed users can stick to their favorite data parallelism without worrying about model parallelism. In contrast, without DeepSpeed, a model with more than 1.4 billion parameters will run out of memory using data parallelism alone. In summary, we developed DeepSpeed to offer exceptional scale, speed, scalability, and good usability. Next, let's take a step further, look at some highlights of the techniques which enable those results. I list them in 3 categories: efficiency, effectiveness, and usability. Efficiency promote efficient use of single device and cross devices. For example, ZeRO Redundancy Optimizer, ZeRO, optimized for memory efficiency. Fastest transformer kernels, optimized for compute efficiency. Sparse gradient for communication efficiency. Overlapping I/O with compute for I/O efficiency. Combination of data and model parallelism for scaling efficiency. Effectiveness promotes for fast convergence. For example, adaptive hyperparameter tuning, optimizers for large batch training, and so on. Usability features make efficiency and effectiveness features easily accessible to our model developers. For example, we set up boilerplate features for distributed training like mixed precision, gradient compression, gradient accumulation, and so on, such that our model scientists can focus on the model design. We also simplify I/O, checkpointing, profiling, which are all essential for large job training. Later on in the talk, you'll see a few of these techniques in more details. This slide shows DeepSpeed software architecture. That's also how we put different techniques together in the software stack. DeepSpeed has 3 parts: API, runtime, and ops. I'll talk about them one by one. DeepSpeed API is a thin layer which is compatible with PyTorch. As you have seen, our key API is DeepSpeed.initialize. And we also have parameter JSON file that allow users to configure their training settings. The second part is DeepSpeed runtime. This is also the core part of DeepSpeed: manage execution, conduct performance optimization. For example, a deploy training job across distributed devices, perform data and model partitioning, conduct system optimization. It also have tuning model for effectiveness and utility model for failure detection and checkpointing. DeepSpeed runtime is written in Python. The third part of DeepSpeed is DeepSpeed Ops. This is our low-level kernels written in C++ and CUDA to optimize computation and communication. Examples are like ultra-fast transformer kernels, fused LAN kernels, custom ORDIs, and so on. Next, I want to talk a bit on the rationale for us to choose such a software architecture. There are 2 parts. First, that we perform optimization on top of the training framework versus closely coupled. By doing that, we can well leverage the entire ecosystem. At the same time, it's far easier to maintain comparing with deep integration. Secondly, DeepSpeed is infrastructure agnostic, so our users can leverage DeepSpeed on their favorite environment like Azure ML, Azure VMs, MPI-based platform, local nodes, and so on. So that completes the overview of DeepSpeed. Next, I'll turn the floor to Jeff to talk about how to use DeepSpeed.
Okay, so today I'm going to talk to you about DeepSpeed and how to use it. And I urge you to check out our website. It's at deepspeed.ai, which is linked here. So specifically, DeepSpeed uses PyTorch models. So what we kind of assume here is that you have an existing user model that's written using PyTorch's NN module. So the documentation's here on the right. This essentially, you have implemented a forward pass and your model parameters and so forth. That's a fairly standard kind of way in PyTorch to express your model. then the next step is modifying your user code to actually use DeepSpeed. So the way that this works is you import DeepSpeed and then you use our initialize function. So this is DeepSpeed initialize, which then wraps your model. This is kind of similar to PyTorch's distributed data parallel in sort of style, but it provides several additional features. So the required piece here is passing in your model, but you can also pass in additional pieces such as optimizer, learning rate scheduler, or dataset if you want to use kind of different features that DeepSpeed enables. The next piece is updating your Python argument parser. So what this will do is it'll modify the parser that you're using to add some DeepSpeed specific flags, and we'll talk more about those in detail coming up. The DeepSpeed initialize function returns a wrapped version of your model that you'll then use for forward, backward, and parameter updates, which we'll go into much more detail soon. Once you have that, then you can use our DeepSpeed launcher to actually execute your training across all your distributed nodes and GPUs. The way that that works is you'll use the DeepSpeed launcher, which will be installed with DeepSpeed. You'll pass in the client, your client entry script and whatever client arguments you have, and then add this flag called DeepSpeed config, which is the configuration JSON associated with your DeepSpeed run, where you can turn on and off various features. An example here is like if you're training a C410 model, it's like just DeepSpeed C410.py and then the DeepSpeed config. But what that buys you is it lets you use DeepSpeed to then train across all of your different distributed nodes. So if you're using 64 GPUs spread across multiple nodes, physical nodes, this will do this launching kind of seamlessly for you. It'll handle the environment propagation, data partitioning, and seamlessly kind of incorporate all of the different system optimizations that we've talked about today and that we'll be talking about soon. So let's look at a specific example. So this is a BERT model. Before we make our DeepSpeed modifications, this is kind of what it looks like. We construct let's say this BERT multitask model, for example. We would traditionally wrap this maybe in a distributed data parallel module. And then after this, we would construct our specific optimizer. And then if we want to do FP16 training, we would wrap this as well. Then after that, we would do our forward pass, backward pass, and optimizer step as shown here. But now after applying DeepSpeed, we construct our model just like we did before, but now we want to actually wrap this with our DeepSpeed initialize call like we were talking about before. It returns a model, and then we do our forward pass, where very similar to before, our forward pass is the same, but now our backward and parameter updates are just slightly different, and they're with respect to the model itself. For more details, definitely urge you to check out this link. What this is it links to our DeepSpeed examples repository that has all sorts of different models that we've modified to use DeepSpeed, such as BERT in this case. The next step here is the DeepSpeed JSON file. So this is this one specifically we would use for BERT. And what this does is it tells DeepSpeed, let's say the batch size that you're training with, so the total batch size maybe of 6,500, or 65,000 in this case, and the training microbatch size. So this is the batch size that you're actually training with on each GPU. So in this case, this is 64 samples that each GPU would be training with instantaneously at that time. And then in addition, what kind of optimizer you're using. So in this case, this is LAM, what learning rate, and sort of what other hyperparameters that you want to use during your training. Then finally, turning sort of on and off the feature of mixed precision. So this is training with FP16, so we could take advantage of all those nice tensor cores that are available on like V100 GPUs from NVIDIA, for example, or that sort of thing. And again, here's our nice link to check out the example if you want to dig into this in more detail. So one more example we want to talk about today is Megatron's GPT-2 model. So this is NVIDIA's implementation of OpenAI's GPT-2. On the left, we have the original version of this that constructs the model, does some FP16 kind of wrapping, distributed data parallel wrapping, just like in BERT. constructing the optimizer, and kind of doing some specific things relating to FP16 training. And then, just like before, the forward, backward, and parameter updates. Now, after applying DeepSpeed, this is what it looks like. So we instantiate the model just like we did before, create our Atom Optimizer, and then just do this DeepSpeed initialize call. And just like before as well, we just do our forward pass just like on the left side, but our backward and parameter updates are now with respect to the model, the newly wrapped model. And we've included a handy link here that links to the modified GPT-2 code in DeepSpeed in our DeepSpeed examples repository if you want to look at the specific code changes in more detail. And then lastly here we have the DeepSpeed JSON file for GPT-2. And what this has is on the right we have the train batch size of 512. We have the Atom Optimizer. FP16 training is enabled, and now sort of one key difference is our ZeRO optimization is set to true. So Samyam shortly will be talking about all the features of ZeRO and how it works, but the nice part is that to turn it on and off is just essentially a flag in the config. So turning it on and off is quite simple. With that, I'll give it to Samyam to take over the rest.
Hello everyone, my name is Samyam Rajbhandari. I am a researcher at Microsoft and I work on accelerating distributed training at a large scale. And today I'll be talking about the DeepSpeed library in the context of large model training. So there are numerous challenges when it comes to training a large model. From a system perspective, on one hand, large models are computationally intensive to train. And on the other hand, the amount of memory required to train these models can be several orders of magnitude larger than the amount of memory available on a single GPU, making it very difficult to train these models. To address these issues, DeepSpeed can significantly reduce the amount of memory required for training, while at the same time it can also improve the training throughput during the training and also reduce the amount of resources required to train these models, making it accessible for many model scientists to train large models. So to give an example, in February of this year, Microsoft trained the Turing-NLG 17 billion. It's a 17 billion parameter GPT-like model, and it was the largest model, largest language model at the time of its training. To just give a quick context of how large this model is, the table here shows the Turing-NLG 17 billion in comparison with BERT large. As you can see, in terms of computation, this model has over 100 times computation than the BERT large. And in terms of memory, just the memory footprint of the model itself and the model states requires about 275 gigabytes of memory compared to 5.12 gigabytes for BERT large. So given this, it was quite impossible to train this model using the state-of-art technology at the time. With DeepSpeed, we were able to significantly reduce the memory footprint and also improve the throughput, as well as reduce the number of GPUs required to train this model, allowing us to go from just being completely infeasible to train this model to becoming practically possible. So I do want to point out that it is possible to train this model without DeepSpeed as well. You could use existing state-of-the-art technology like tensor slicing or model parallelism, such as the one that is implemented in Megatron to train this model. In model parallelism, you split the model states across multiple GPUs during the training, and each GPU is responsible for doing part of the computation, and it only holds part of the model parameters, which allows you to train the model without running out of memory. So here in this table, we're showing the configurations required to train this model using the state-of-the-art model parallelism framework called Megatron. Here you can split the model with a 16-way model parallelism on a DGX2 node. These nodes have 16 V100 NVIDIA GPUs. Each one of them have about 32 gigs of memory. So even after splitting the model into 16-way model parallelism, we could only fit a batch size of 8 per node. So given this high level of model parallelism and a small batch size, the amount of computation that is being done on each GPU is too small to be efficient. So you can see that the throughput per GPU that we could achieve during this training was about 9 teraflops. To put this in perspective, these V100 cards have over 120 teraflops in peak performance, so it was achieving less than 10% of the peak performance. And to add to that, these GPT-2 style models are usually trained with a batch size of 512 or larger, and given that we could only fit a batch size of 8 per node, this means that you would need 1024 GPUs to just be able to train with a batch size of 512. And so given this prohibitively large amount of GPUs required to train this model and this really inefficient training, it was quite infeasible to train this model. So DeepSpeed addresses this issue using a memory optimizer in it called the ZeRO Redundancy Optimizer. With ZeRO Redundancy Optimizer, we are significantly able to reduce the memory footprint for this training, allowing us to train the same model with just 4-way model parallelism instead of 16. And with that, we are able to fit a batch size of 32 per node. And so now, because you have smaller model parallelism degree and a larger batch size, we can get a much higher efficiency per GPU. So we're able to achieve over 30 teraflops of performance per GPU. So that's a 3x improvement in throughput. And now, since we can also fit a 4 times larger batch size of 32, we only need 256 GPUs to fit the batch size of 512. So with this, it was possible to train this model. So the next natural question is, how does the ZeRO Redundancy Optimizer reduce the memory footprint? So before we get there, let's first talk about the standard data parallel training that is usually used to train models across multiple GPUs. So in standard distributed data parallel training, we are trying to train the data parallel training loop that is shown on the left side of this slide on a distributed GPU cluster where this loop is being executed on each one of the different GPUs. Each GPU loads a different mini batch. It also has the model states that are replicated across all the GPUs, and so each GPU executes the forward pass, computes the loss on its mini batch, then it computes the backward propagation to get the gradients. Then these gradients are averaged across all the GPUs. Once these gradients are averaged, each GPU then in parallel computes the updates to the model states and the model parameters. Then it applies those updates to its model parameters, and that completes one iteration of training. So here, the figure at the bottom, the first row shows the memory map while training a model using distributed data training. The first row shown in blue represents the memory consumed by the parameters. The second row in orange shows the memory consumed by the gradients, and the big chunk in green shows the memory consumed by the optimizer states. So this could be for an optimizer like Atom, it could be your momentum and variance. And if you are training your model in mixed precision, then it could also be a 32-bit copy of the parameter themselves. So the key thing to note here is that these optimizer states, gradients, and parameters, which we collectively call the model states, they are replicated across all the different GPUs in distributed data parallel training. So the way ZeRO works is by removing this redundancy across these GPUs. So since there are 3 different types of model states, there are 3 different phases of ZeRO, each one of them removing the redundancy for one of these states. So for example, the first stage of ZeRO removes the redundancy in optimizer state. That's shown in the second row. The second stage removes the redundancy in the gradients, and the third stage removes the redundancy in optimizer states, gradients, as well as the parameters. And it removes that redundancy by simply partitioning these model states across GPUs instead of replicating them. So here, to just give a flavor of how ZeRO works, we're going to dive deeper into stage 1 of ZeRO. So stage 1 partitions the optimizer states instead of replicating them. In terms of computation, everything works quite similar to how things work in standard data parallel training, where each GPU loads up its own mini batch. Then it performs a forward propagation and backward propagation on that mini batch. During the backward propagation, each one of the GPUs is computing its gradients with respect to that mini batch, and then those gradients are averaged. Now, after that, instead of each GPU updating all the parameters, each GPU only updates a small portion of the parameters, a small partition that belongs to that GPU. Once that partition is updated, then the GPUs perform an all-gather operation so that these updated partitions can be sent to all the remaining GPUs so that each GPU has its entire set of parameters updated. So that's ZeRO stage 1. Let's take an even deeper dive into this. So let's say we're trying to train a transformer-based model with 16 transformer layers, like a BERT large, across 2 GPUs, right? So the cells here shows the memory footprint of for training this model for standard data parallelism. On each GPU, you have memory to store the FP16 parameters. So here I'm talking about a mixed precision training, which is the standard way of training these GPT-2-like models on modern architectures, which have significantly improved throughput for computation using these FP16 data types. So you have these FP16 parameters, then you have the FP16 gradients, and then you have your optimizer states in FP32. So if you're using an atom optimizer, then you may have your momentum and your variance. You may also have FP32 gradients and FP32 parameters. And of course, to train the model, you also need memory to store your activations. So this is standard data parallelism. With ZeRO stage 1, you partition the optimizer states across GPUs. So each GPU only keeps half of the optimizer states. Then, just as standard data parallelism, you perform forward propagation through the transformer blocks. You compute your loss, and then you compute your backward propagation and compute your gradients. So now, once the gradients are computed, since GPU 0 only needs to update the first half of the parameters and GPU 1 only needs to update the second half of the parameters, GPU 0 will receive the first half of the gradients from GPU 1, and GPU 1 will receive the second half of the gradients from GPU 0, and then each one of these GPUs can then average these gradients. Then using these average gradients, now each one of the GPUs can update its model states, then it can update its parameters, and once the parameters are updated, now you perform an all-gather where GPU 0 sends the updated parameters from GPU 0 to GPU 1, and GPU 1 sends the updated parameters from GPU 1 to GPU 0. And so that completes a single iteration of training using the ZeRO stage 1 optimizer inside DeepSpeed. Okay, so now coming back to training the Turing-NLG 17 billion, this model was trained using ZeRO stage 1, and stage 1 can provide up to 4x reduction in memory. It was trained using a combination of ZeRO stage 1 and model parallelism, and the reason why we can do that is because ZeRO can work with tensor slicing based model parallelism frameworks such as Megatron LM. And the way it interacts with this model parallelism implementation is through a simple API that requires the model parallelism framework to pass in a model parallel unit object. all that object does is implement these two methods. The first one, the get data parallel group, that returns the list of GPUs that are involved in data parallel training, and the second one, called get model parallel group, that simply returns the list of processes that are involved in model parallel training. So DeepSpeed and ZeRO does not need to know how model parallelism is implemented. It just needs to know which GPUs are involved in model parallel training, and as long as you can get that information, DeepSpeed and ZeRO will work with model parallelism. So with that, here's a recap of the results. Using ZeRO with Megatron, we were able to reduce the model parallelism degree by a factor of 4. We were able to increase the batch size also by a factor of 4, which meant that we can reduce the total number of GPUs required to train the model from 1024 to 256. And by decreasing the model parallelism degree and increasing the batch size, we were seeing over 30 teraflops in performance compared to 9 teraflops when using Megatron alone without ZeRO and DeepSpeed. So as we mentioned earlier, ZeRO actually has 3 different stages. The first stage, as we saw earlier, it reduces the memory by up to 4 times. With stage 2, we're able to further reduce the memory by 8 times. And with stage 3, you can reduce the memory proportional to the number of GPUs that you are using. And all of this memory reduction comes from very modest to no increase in the amount of communication volume during the training. So for example, with stage 3, you're increasing the communication volume by about 50% compared to the standard data parallel training. However, with stage 1 and stage 2, you're getting up to 8x reduction in memory without any communication overhead. So the communication is exactly the same as in standard data parallel training. So currently in DeepSpeed, we've implemented stage 1 and stage 2, and what this allows you is to train models with up to 13 billion parameters without requiring any model parallelism, and it can train models with up to 200 billion parameters when combined with model parallelism on today's GPU clusters, such as the DGX2 clusters with 16 NVIDIA V100 GPU cards. So far we've been talking about ZeRO and how it reduces the memory by partitioning the model states. In addition to reducing the memory from model states, ZeRO also has a bunch of more optimizations that allows reduction in memory from other components. So for example, just like how model states are replicated across multiple GPUs in data parallel training, activation memory during training can be replicated across multiple GPUs during model parallel training. And so ZeRO can remove the redundancy in activation memory by partitioning the activations across these model parallel GPUs. You can also offload these activation memories to CPU if you don't have enough memory to train extremely large models. The next optimization that ZeRO can do is convert fragmented memory to defragmented memory on the fly during training. So during training, if your memory is fragmented, you might still run out of memory even when you have enough memory available during the training, just because you can't allocate a single contiguous buffer to satisfy a memory request, even though there might be enough fragmented memory that can satisfy the request if they were contiguous. So in ZeRO, the memory defragmentation will on the fly defragment these memory fragments so that all the memory is contiguous and you are able to satisfy these larger memory requests. So with all these different memory optimizations, with the second stage of ZeRO model state optimizations, we are able to train models with up to 200 billion parameters, up to 10 times faster than current state of the art. We call this implementation ZeRO Stage 2, which is already in DeepSpeed. Next, I would like to ask Tunji to talk about the second use case scenario for DeepSpeed by presenting the world fastest BERT training. Thank you, everyone.
Hi, I'm Tunji. I'm a researcher at Microsoft. I work on system support for large-scale deep learning. Now I'm going to be talking about how we achieve the world's fastest training time on the BERT large model using the DeepSpeed library. So with using DeepSpeed, we're able to complete training the BERT large model in 44 minutes on a 1024 NVIDIA V100 GPUs. Compared to the previous published record of 67 minutes that was reported by NVIDIA using the same number of GPUs of the same generation. This table here goes into a bit more details about our scalability. As you can see, we are able to scale close to linearly as we increase the number of nodes from 1 to 64. So in terms of the technology in DeepSpeed that allows us to achieve this training time, there are basically two aspects to them. One, there are efficiency optimizations which target single GPU performance, and this collection of optimizations enable us to achieve over 50% of the peak throughput on an NVIDIA V100 GPU. The second class of optimizations are the effectiveness optimizations. These are techniques that allow us to converge on large batch training using fewer samples. So collectively, these optimizations, the convergence optimizations, allow us to converge with 422 million samples compared to the baseline of 512 million samples. The efficiency optimizations that I'll be talking about today include optimized transformer kernels, overlapping I/O with computation, and sparse output processing. The effectiveness optimizations that I'll be talking about include the fact that we train using mixed sequence length training with a batch size of 64K, a LAMB optimizer, learning rate schedules, and pre-layer normalization. So first, I'll talk about the single GPU optimizations, specifically the kernel fusion. Here I'm showing an image of the transformer block, highlighting the various computations in the transformer execution, such as the query, key, and value matrix computations, which are highlighted using these colored blocks. So each of these blocks involves a CUDA kernel call, and each call comes with its overhead. And so the idea behind kernel fusion is to derive a number of benefits. The first of which is to reduce the kernel call overhead by having fewer kernels. The second benefit is that by fusing kernels together, we increase the amount of work that's done within each call, which helps to improve the GPU utilization. Another benefit is that some of these kernels have same input data which have to be read from global memory. And so by fusing them together, we can get away with reading the data only once rather than repeatedly, which helps to improve the data locality and simultaneously reduce the memory bandwidth requirements. Within the transformer for BERT, we identified two classes of candidate kernels for fusion. The first class of kernels are the parallel kernels, such as the query, key, and value kernels, which execute independently and so can be fused easily. The second class of kernels are the producer-consumer kernel, such as the dropout and residual input, which are added together and fed into layer normalization that goes into the feed-forward. This can also be fused easily. So now I'll go into an example of how we fuse the QKV kernels and thereby improve data locality and reduce memory bandwidth requirements. Here on the left, I'm showing the baseline QKV kernels and also the transform versions of these kernels that as executing in the PyTorch code. The blue lines here are representing the data flow during the forward pass, and the red lines are representing the data flow during the backward pass. On the right-hand side, I'm showing the fused kernels within DeepSpeed. And here we can see a number of differences. First, we see if we focus in on the forward pass, we see that rather than have 3 reads of the input into the individual kernels, we can reduce that to just a single read. Similarly, on the backward pass, rather than having the QKV kernels generate 3 writes to global memory, we can reduce that to a single write to global memory. In this way, we're improving the data locality and reducing the bandwidth requirements on global memory. The other class of single GPU optimizations we have involve the invertible operations. Invertible operations are the ones where the backward pass is independent of the input. And in transformers, we identify 2 classes of such operations, the softmax and layer normalization. The benefit of invertible operations is that they can help to reduce the activation memory footprint because we no longer need to save the input activation memory on the forward pass to be consumed on the backward pass, since the backward pass is independent of the input. Another benefit is that invertible operations can also be easily fused with other operations, and so we do not need to save intermediate results in the cases where they have a producer-consumer relationship with other operations. So here I will illustrate an example using the invertible softmax. On the left, I'm showing the baseline softmax computation graph in PyTorch. And what I'll draw your attention to is the fact that on the input we have to save the input activations, which are represented with the x1 to xn tensors. And on the output, we're saving the output softmax, which are the S1 to Sn tensors. If we compare this to the computation graph in DeepSpeed, we see that we no longer need to save the input activation because we can reformulate the computation, the softmax computation, to become independent of the input. So we can compute the gradient without relying on the input. And so this allows us to avoid saving the activation and thereby save memory. The other single GPU optimizations that we have include overlapping of I/O and computation and sparse output processing. Let me briefly talk about those. For the overlapping I/O and computation, what we do here is we prefetch the next input batch into CPU while the GPU is processing the current batch. By doing this, we're able to avoid the data loading and tokenization overheads that is required. We're able to move that off the critical path so that when it's time to process the next input batch, we are simply just moving from CPU to GPU, which is a lot faster than if we were reading directly from disk. The second optimization is the sparse output processing. So in the output, we observe that only 15% of the mass tokens are actually required. And so there's significant sparsity in the computation. This output, of course, is then fed to the projection and cross entropy is performed on it, but we do not need to do this for all of the available tokens, only for the masked ones, which we observe to just be 15%. And so this is what this optimization looks like. So first on the left is, we can imagine, is the initial output. And by applying this mask on it, we're able to shrink the output down into smaller size. In particular, for BERT, we observed that we are able to reduce computation by 85% using this optimization. So combining all of these optimizations together, we're able to improve the performance for BERT training, both on the sequence length 128 and sequence length 512. First, I'll be showing the single GPU results for the sequence length 128. Here, we can observe that we're able to train with larger batch sizes, 80% larger batch size compared to NVIDIA kernels. Also, we're able to train at 26% faster throughput compared to the NVIDIA kernels. On the sequence length 512 results, we observe similar improvements. We're able to train with 80% larger batch size compared to NVIDIA kernels, and we're able to train at a 28% higher throughput compared to the NVIDIA kernels. Now I'll switch to the convergence tuning optimizations which help to improve the effectiveness of our training. The first class of these optimizations has to do with the LAMP optimizer. So LAMP optimizer is a layer-wise gradient adaptation optimizer which basically tries to clip the gradient values within a range. And in our implementation of the LAMP optimizer, we make it possible for users to configure the min and max coefficients for the clipping. And here I'm showing exactly the values that we use for our training. Here I'm also illustrating what the histogram of the gradients look like for the sequence 128 and sequence 512 training. And here we can see that the optimizer is able to clip and keep the gradients within this specified ranges. The second class of convergence tuning optimization has to do with the learning rate schedule. So here we found that using a cyclic schedule with decay and doing a rewarm up when we start the 512 sequence length portion of the training is very effective to enable us to get convergence using fewer number of data samples. The last class of convergence tuning optimization is the layer normalization. So layer normalization is a technique for improving training stability when we train at very large batch sizes. It helps to avoid vanishing and exploding gradients. Layer normalization can be applied before or after the attention layer. And when it's applied before the attention layer, we refer to that as pre-LN. And if it's applied after the attention, we refer to that as post-LN. It turns out that the placement is pretty significant. It has a significant impact on convergence. And so here we're showing on the right-hand side the plot comparing the pre-LN versus the post-LN. And as we can see, if we apply post-LN, the model actually diverges pretty early on during the training. But with the pre-LN layer normalization, we're able to train effectively even for a batch size as large as 64K. So in summary, we're able to achieve the fastest training time with BERT using the DeepSpeed library. And this is possible using two directions of optimizations of efficiency and effectiveness. And the fact that these two optimizations are independent means that we get a multiplicative effect by combining them. So in summary, the efficiency optimizations enable us to achieve 50% of the peak throughput on an NVIDIA V100 GPU. And on the effectiveness side, this allows us to train with 18% fewer data samples using 422 million samples compared to the baseline of 512 million samples. And the great thing about this set of optimizations is they are widely applicable across models beyond BERT. They can be applied to all transformer kernels. Before I round up, I'd like to tell you about some interesting upcoming features that we have in future releases of DeepSpeed. The first one is the ZeRO Stage 3, which Samyam talked about earlier. Here we'll be able to achieve a linear reduction of the memory footprint of parameters corresponding to the data parallelism degree of our training. This will enable us to train trillion parameter models using commodity hardware. The second class of features that you can look forward to in DeepSpeed are the sparse transformers. Sparse transformers will enable us to train sequences that are 10 times longer than is currently possible today, and we'll be able to train them 5 times faster than is possible today. For more new and exciting features, you can go to our repo on GitHub or check out our breaking news page and documentation on our website, www.deepspeed.ai. So this brings us to the end of this webinar. Thank you very much for your attention, and we look forward to taking your questions in our live Q&A which follows on.
Hello, everyone. Thank you for attending the DeepSpeed webinar and our live Q&A. We have 4 members of DeepSpeed team here. I'm Yuxiong He.
Hi guys, my name is Samyam Rajbhandari. Thank you for tuning in.
Hi, I'm Jeff Risley. Thanks for tuning in.
Hi, I'm Tunjiro Washe. Thanks for joining us today.
Over the next 20 minutes, we are going to answer top questions submitted by the audience. Let's get started. Our first question is, when does ZeRO show memory and throughput improvement? Does ZeRO have a huge performance penalty?
So, hi guys, I'll take this question. ZeRO can show performance improvement in several different scenarios. One of the scenarios is recently, I'll talk about both DeepSpeed as well as ZeRO. On the DeepSpeed side, recently we released the transformer-based kernels. So if you are using any transformer-based model, DeepSpeed is going to give you a significant performance improvement. On the ZeRO side of things, ZeRO will show you a big performance improvement when your model is really large and you cannot fit the model. In a lot of cases, when you are just using standard data parallelism, you can't even train a model with over 1 billion parameters without requiring significant changes to the model itself using things like model parallelism techniques like Megatron. But with ZeRO, you can just use your standard model that you created in PyTorch, and ZeRO can partition those models and reduce the memory footprint, allowing you to not only run these models, but also run these models at decent batch sizes, which gives you significant computation efficiency, allowing you to get the speed up. And so one common question that we see a lot is, what about the overhead of communication that ZeRO incurs? Is it going to perform worse than standard data parallelism? And the answer to this question is that if we consider ZeRO stage 1 and stage 2, which is what is currently in DeepSpeed, there is actually no additional communication overhead of DeepSpeed and ZeRO compared to standard data parallelism. So there's going to be no loss in performance compared to standard data parallelism for smaller models. And for larger models where you can't train the model with data parallelism, or even when you can, the throughput is really slow because of a small batch size, ZeRO can significantly improve the performance in those scenarios.
Thank you, Zheyan. Our next question is, do we need to specify the hardware configuration and binding while training, or DeepSpeed handles it automatically from inside the module? Jeff, would you like to take this question, please?
Sure. Hi, everyone. So in terms of how DeepSpeed essentially is able to discover your environment, is we rely on PyTorch to give us essentially access to the GPUs or CPU in some cases, but you don't really need to specify much of anything of your hardware level environment. What we do sort of assume, and I urge you to check out our documentation for some additional details, is connectivity between machines. So if you're trying to scale out your training to multiple nodes, then you'll need to set up essentially passwordless SSH between the nodes. This is similar to kind of requirements in like MPI environments and so forth. But once you have that piece set up, then DeepSpeed's able to essentially scale out the training for you and communicate across all the different nodes and so forth.
Thank you, Jeff. Our next question is, does DeepSpeed support single GPU or only for multiple GPUs? Tenji, would you like to take this one?
Yes, I will, Yuxiong. Thank you. Yeah, so DeepSpeed provides benefit at pretty much every scale level. So from a single GPU scenario to a single node which has multiple GPUs to a multi-node and scenario, DeepSpeed provides benefits, performance, throughput benefits at every level of the scale. And so for a single GPU, for example, we have basically optimized kernels that helps to improve the single GPU performance. beyond what is normally possible with other frameworks. And also we have techniques such as overlapping of the I/O and computation, which also improves the single GPU performance. Within a single node, we have our distributed training framework is highly optimized so that it helps you get the linear scaling within a single node. And when you go across nodes, where techniques such as model parallelism starts to hurt when you have to cross nodes. The ZeRO optimizer helps to reduce the need for model parallelism that has to go across nodes, and so that way you can get close to linear scaling as well as you go across nodes, even for very large models. And so so regardless of what your usage scenario is, DeepSpeed has some benefit for you in terms of improving the throughput for your training workload.
Thank you, Tenji. Okay, yet another one. What types of models can benefit from DeepSpeed? I saw that most examples are NLP models. Would DeepSpeed work for image models, GAN types of models, machine translation models, LSTM models? Sayan, would you like to take this one, please?
Sure. So there is nothing special about the NLP model that we are targeting in DeepSpeed. The optimizations that we've developed are fully general, and they will span across all different types of models. For example, our communication backend is optimized, so if you have, for example, sparse embeddings, you can use the DeepSpeed sparse communication to optimize those. Anything that uses a transformer kernel, you can use transformer both on the image side and on the NLP side. You can take advantage of the optimized kernels in DeepSpeed library to speed those up. If your model is too large, then ZeRO will work regardless of whether it's an NLP model or something else. So basically, we've identified the common DL training pipeline that is common across all these different types of models from different domains, and we've optimized those so that when you do switch across domains, those optimizations will still help.
Thank you, Sayan. Okay, yet another question. What training data set do you use for BERT pre-training, and how do I get access? Tenji, would you like to answer this one?
Yes, thanks, Yuxiong. So for the BERT training data set, we initially internally used like an internal data set, but recently in our latest release, and it's available now in our GitHub, we provided the ability to use the NVIDIA data set for BERT training, the BERT training data set that comes from NVIDIA, which is open source. So if you go to our GitHub, you would be able to do that right away. We have already provided instructions for doing the end-to-end training with this data set, and so there shouldn't be any blocker concerning that.
Thank you. It looks like that we have time for one more question today. Okay, here is a question. Can I use the fast transformer kernels on other models beyond BERT, and how do I do that? I guess, Tenji, that you are going to take this question again.
Sure. So the fast transformer kernels can benefit if you have a BERT-like or transformer type model, because the optimizations there are specifically targeted for the transformer kernels. And so if you do have any kind of sort of transformer model, you'll be able to take advantage of this optimizations. And in terms of how you will use it, you can we have documentation of how we've applied this to the BERT model, and that could be a starting point for you to start using it for your own model. And as always, we are always available to help if if your own models deviate in some way or the other, we're very responsive on our GitHub, and so you can. We definitely would like to hear back from you if you have any issues that come up as you apply this optimized kernels. But they're designed to be generally beneficial for transformer type computations.
Thank you. And thank you all for attending today. We appreciate your participation and interest in DeepSpeed. If you'd like to learn more, or even better, try out DeepSpeed, please visit our website, deepspeed.ai, and our GitHub repo. So these links are provided in the resource list to the right of your screen. In the resource list, there are also links to our technical paper and blogs. We look forward to hearing your feedback. We hope that DeepSpeed makes the training of your exciting deep learning models easy, efficient, and effective. Thank you, and have a great day.